Yes, done. All right. As usual, I suppose there's no issue with my voice and with my screen. I am actually sharing my screen with you guys. So if you cannot see it, please let me know. And also, if any issue with my voice, let me know. All right. Okay. So according to the proposal, so these are the question for tutorial 4 proposed by your class coursemate to discuss, right? So 2, 3, 6, and so on. All right. For these questions, I'm not sure whether I need to discuss this or not. Okay. This is because I have discussed it in chapter 4. Okay, so you refer back to lecture for chapter 4. Okay. So because I have actually discussed this question 10 as an example. Okay, so please refer back to it. So if you want me to go through it today, so you just let me know, right? Otherwise, I will just leave it. Okay. Okay, all the questions over here. Question 9. Okay, yes, this are the question. Okay, let's start off with question 2. Again, I'm not sure what's the issue with question 2. Okay, because I suppose if you have no problem with question 1, then you should have any issue with question 2. Okay. So I assume you have no problem. Okay, maybe I briefly go to the solution for question 1, okay, and then I proceed to question 2. Okay, so this maybe I again just 1 minute. So this is the questions. Okay. All right. So this is the questions, and I just copy and paste the solutions. Yeah, here is it. So this is the answer for question 1, right? So this is the solutions. Okay, first of all, for question 1, we just need to verify that x is equals to this. We submitting the indicator function corresponding to the set a is greater or equals to k. Okay, so I maybe just go through it step by step. I hope this will be clear. Okay, so what we can do is we verify each of the domain omega. Each of the omega in the domain. So please note that in this case, x is a integer value, random variable, and positive integer. So which means the value of x will be taken for 1, 2, 3, 4, 5, and so on. Okay, so that means x of omega will be an integer. Okay, let's take 1 omega in the domain. So and x is equals to n. Okay, so I think this is quite okay. What you can do is, for example, you can assume, okay, let's look at a special case. So for example, if we look at an easy case, let's say this is 4. Okay, let's S omega is 4. So X omega is 4. That means omega must be belongs, X of omega must be greater than 1 and greater or equal to 2. And if we carry on, that will be which is omega also belongs to X greater or equal to 3, as well as omega belongs to X greater or equal to 4. And because of, if we set X omega is 4, this is just an example, okay, just for example to illustrate the ideas. So when this is 4, so we have this. So then after that, omega will not belong to this, okay? Because of X omega is 4, so it does not belong to this anymore. So that's why what you can do is we stop here. You can forget about all those things, okay? So that's why in this case, when we take n is 4, so that means omega only belongs to 1, 2, 3, 4 of them, okay, in this case. So then we can check this easily. So then this must be equals to 1, x greater than 1 until x greater, for this case, that will be 4, okay? So and this one, if 5, this will be 0. Okay, I think maybe I will just, it's better I write it out. Okay, got it. I think I better I write it out better. Okay, so maybe I just give you 1A. So I just give you the idea for n equals to 4. Okay, just to give you the idea. So you can see if x of omega is equal to 4, so this is equivalent to say that. Take away this. This is equivalent to say that omega belongs to this. Omega belongs to this. I think maybe 3 would be good enough. Yeah, there's a 3. So 3. So omega belongs to 3. And so on. Omega will not belongs to this x greater than 4 anymore. Yeah, so that's why we will not consider it. So omega belongs to this, then we can see one of this must be equals to 1. Yeah, and the next one of, refer to this set x equals 2 of omega again. This is also equals to 1. And for this, 1 of omega corresponding to this event must be also equals to 1. But when we come to here, 1 of this omega, because of we can see because of the value here is equal to 3, so that's why this is 4, so that's why it does not belong to here, so this must be equals to 0 and so on. So from here you can see this, then we look at it. So if we take the summating of k running from 1 to infinity of 1 of this. So that means we only take the first 3. So that will be equal to 1 plus 1 plus 1. And plus the remaining will be all 0, 0, 0, and so on. So for this case, then we can get this will be equals to 3. So if you compare these two, so this is actually our left-hand side. So this is actually our right-hand side. So from here, you can see left-hand side always equals to the right-hand side. So then we claim they are the same. Yeah? So we can see since the left hand side always equals to right hand side for all omega. Okay, then we can make the claim. Hence, x must be equal to this. So that's the way to do it. So the solution is actually the general one. So we consider n. So actually, this method is applicable to all positive integer n. So I just use n equals to 3 to demonstrate the process of the solutions, right? So if you can follow this, then you should be able to follow the general case. Okay, so this method is applicable to all positive integer n. So this is the solution for question 1a. So for question 1b, I just put over here. Okay, so I think 1b I will just follow here. You can check it out. So this is the solutions. So for 1a, we can calculate. So 1b, so this one, we can split it up. So this is directly we can do. Okay, what you need to take notes will be this. Okay, maybe I just further explanation about it. So if you look at this part, so this will be equals to, we can take out of 2, summating k equals to 1 of k. Okay, minus, okay, this is equals to, because this is up to n, and minus summating k equals to 1 of 1. Okay, so okay, next, you just need, this is clear, and then it's clear, this is clear, this is equals to n for this part. I think no problem. So this part will be always equals to n, no problem. And next, this one, this is actually equals to this n over. Okay, so this is equals to this one. So how to do this? So this is again, so you refer back to calculus. Okay, back to calculus. What do we call it? I think this is so-called the arithmetic series. Okay, the formula. So you can have it's not arithmetic series. I think I can't remember. Okay, it's not. I think maybe you can just go back to refer to a formula in calculus. So I think you should have seen this before. Okay, we taking summating this will be n over n plus 1. So this is how we can get these terms and this term here. Right. So if you're able to get to this step, so you should be able to get answers. So as again, left hand side, right hand side are identical. So we claim that the formula is true. Okay, so this is for our question 1. So for question 2. Okay, air is actually straightforward. Okay, so this is because of we know this x is equals to this summating one of this x greater than equal to k. Okay, this is from question 1. This is from question 1. Okay, so and after that, if we take ex both sides, okay, oh no, I think we have to maybe we will go to one process first. We will do it one by one. Okay, we just do the step one by one. Okay, then yeah. So what we can do is first we can write this xn to is this summating k from 1 to infinity 1 of x greater or equals to k. Okay, so then we have this xn are simple random variable for each for all n. Okay, and also 1 and 2 limit of xn n to infinity will be equals to x. Okay, so this is because of when you take n to infinity, so and this will be just becomes infinity summating of k equals to 1 this. So this will be equals to x. So what we concern will be this limit of this is equals to x. Okay, and I think it's clearly, and also each xn will be less or equals to x. So this is right. So we get these three. First of all, x is a simple random variables. Okay, any xn less or equals to x, and thirdly, limit of xn will be equals to x. So and then when we have this, then by definitions, okay, e of x will be equals to limit of e of this xn. So this will be equals to limit of n to infinity of e of these indicator functions. Oh, sorry. We call it simple random variables. Then we can see e of x will be equals to this p of x greater or equals to k. So ex will this. But we know this. I didn't put it right. Okay. But we know this. Ex is equals to this. For discrete random variables. Okay, we know this. So hence we get the answer. Okay, so this one must be equal to this.
But can it be a simple random variable? It's not a disjoint.
Which one? Come again.
So you know how you define xn as a simple variable, random variable? Yeah. So doesn't the set in you know the indicator, the set for the indicator function, doesn't that have to be disjoint?
Oh, okay. In fact, it is not necessarily to be disjoint. However, when we want to do the calculations, it will be better we express it as a disjoint. So in fact, we can always rewrite the combination, linear combinations for it. into the destroyed form. All right, so maybe I give you examples. Okay, I give you examples for that. Yeah. Okay. By the way, I think this is the way to get it right. Okay. Just a remark for you guys. Okay. For simple random variables. Okay. So just to let you know, there are more than one representations. So that means we can express it in different ways. Okay. So, but however, the expectation value, okay, for each representation are the same. Okay, so these are the same. So this is because the reason is because of we can always switch back to the representations with corresponding to a partition. Okay, so we can always do that partition. Okay, maybe I give you examples. Just give you examples. We can always rewrite it in terms of the indicator function. So just give you examples, right? So for examples, let's say we take, okay, make it easy. Let's say we just take, make things easier. Let's say we just take our omega 1, 2, 3, 4, 5, 6. Okay, 6 of them. Okay, 1, 2, 3, 4, 5, 6. Okay, so so first representations, what we can do is, first representation we can take, let's say A to be 1, 2, 3, 4. Okay, and A1 maybe A1, and then you can take A2 to be 3, 4, 5. Okay, and A3 to be 5 and 6. Okay, maybe 4, 5, 6. Make it worse. Okay, 4, 5, 6. Okay, you can take 4, 5, 6. Okay, we can take this and we take our X to be any number you like, or maybe 7, 1 plus 2 plus 3. Okay, right. This is the one. So from here you can see, so this is the case. Maybe if you look at here, right, what you can do is you can actually split this into another representations. So in this case, then you can see you can change to representations with a disjoint set. So for example, so this is a 1, 2, 3, 4, 3, 4, 5, 4, 5, 6, right? What we can do is we can make it disjoint. So we just consider 1 to 2, 3 to 4, and then 3 to 5, and then 6. So another representation will be this. We can take, let's say, B1 to be 1 to 2. Okay, maybe I use the other color so that you can see the difference. One to 2, and then I can take B2 to be 3, 4, 5. So this is actually exactly same as our A2. Am I right? 3, 4, 5. Yes, and then I can take B3 to be 6 on it. So for this case, right, you can see B1, B2, B3 destroyed. Okay, so these three actually form a partition for it. So from here, we see the difference. Maybe what we need to do is we just need to make things easy. We just need to identify the value for our x. Then you can see a better picture. So in this case, let's say omega and x. So I have 6, right? 1, 2, 3, 4. I'm sorry, I shouldn't put such a large number. When omega is 1, so the value is 7, right? So I think it's quite clear. When omega is 2, it only belongs to here, so it's also 7. When omega is 3, so it actually belongs to here and here. Okay. Okay, so it belongs to here and here. Just maybe a 1, 2, so you get 7 and 7. So when you look at omega is 3, so that is here and here. So you have to sum up these two, so the value will be equals to 9. Okay, so just take it. Okay, and next for omega equals to 4, it's go through this value 4, 4, 4 here. Okay, so that means you have to sum them up 7 plus 2 plus 3. So that's why the value will be 12. Okay, likewise, 5 will be 2 plus this will be 5, and this will be 6 will be 3. Get it? Okay, so this is how we can compute the value for our x. Okay, so if we change to b, so actually we can express it in terms of b. So what we can do is, I think we can follow it in the easy way. That is actually more easier. So 7, 7, 9, 12, 5, 6, 0. Okay, you can look at here, 7, 7, 9, 4, 5, 3, right? So actually we can cut into more instead of this. So what we can do is we can just follow the value here, and then we do a new partition. So 7, 7. So what we can do is we can take B1 to be 1 and 2 only. B2, we just follow the value here. B2 to be 3. B3 to be 4, and B4 to be 5, B6 to be 6. Okay, we just base on the value here, and then we cut it. Then we can see x is actually equals to 7, 1b1 plus 9, 1b2 plus 12, 3 plus 5 plus 6. So you just need to compare. Look at this. These representations is different with these representations, right? These two not the same. However, you can see after that, if you put in the value, you will get the same value. Okay, so the only difference will be the first representations we are referring to non-disjoint set, but for the second representation, we corresponding to a partition, a disjoint set. Okay, so we can always rewrite it in terms of the disjoint partition, what do you call it, a representation corresponding to a partition. That's the way. Okay, so that's the way. That's why it will be easier if we take this representation. If you want to compute the expectation value, that will be easiest. Not easy, easier. Not really easier, but at least we have a better picture, the value for x. Okay. So it doesn't matter. We can switch the representation. So this is the meanings over here. So there are more than one as representation. But the expectation value are the same. You can see, you take the expectation value for this representation and this, they will give you the same value. Okay. Right? But however, in theory, we always say we put it in this way for convenience. Yeah. Right? Okay, so I hope that helped you to get a picture.
Sorry, doctor.
Yeah.
Can you scroll up a bit for the proving part?
Which one?
The 2A.
Solutions here.
Yep. Okay, I'll stop here.
Okay.
For the expectation, the second line and the third,
Yeah.
how the limit ends to infinity e, then the summation the I will be equal to the below one.
You mean here to here?
Yeah.
Oh, here to here.
Yeah.
Okay, here to here. How? Okay, I will just display here to here. Sure. Okay, maybe you refer to your lecture notes, okay? Because I'm running out of space. I'm running out of space. Okay, so just refer to your lecture notes chapter page. What page is it? Oh. Where is it? Okay, maybe I think it's a lecture notes chapter 4, page 1, something page 1 or page 1. Okay. Yep, I got it. Theorem 4.1.3 again. Yeah, refer back to theorem 4.1.3. Yeah, so. Okay, you refer to theorem 4.1.3. Okay, so for this, this is actually saying that I have to maybe I put it over here. Theorem 4.1.3. Okay. So there are two formulas. So first one will be E of, if I have two simple random S1 plus S2. So this is actually E of S1 plus E of S2. So if we apply this, so actually we can apply this up to M of them. So that's why this step will be equals to limit n to infinity of summating this. I think this is quite straightforward. Okay. Okay, by using this A. So I got it. So this one, n to infinity. So this is actually, that's why this is how we get infinity here. Okay. Okay, next we have B. B says that E of indication 1A is equal to P of A. Right? So that's why this one will be equals to, so limit n to infinity, so to n to be summating k from 1 to infinity. I think it's clear. So that's why this one will be, oh, this is how we get it. Right, so I think we're using this. So then this will become, I think it directly come to here. Okay, using part B. So this is by theorem 4.1.3 B. So this is by theorem 4.1.3 A. All right. Just make use of the property of the expectation value. I think you guys are quite familiar with. This is actually linear. I think maybe this is the one you guys have to take note. Yeah, take notes for this. Okay, this one. Right. Okay. Maybe I find a place to write properly. Okay. This is the one. No more space. Okay, doesn't matter. I think the next B and C should be okay, right? So if you can follow the proof for 2A, I think 2B and 2C should be straightforward, huh? Because it's actually follow the same techniques. Yeah. Right. So okay, let's go to question 3. One by one. Okay, so let's just look at A first. All right, so first of all, if we have a random Poisson distribution, so I think first of all, we know the mean is actually lambda, and I think as well as the variance will be also equals to lambda. Okay, so these two are the same. Am I right? Yes. Yeah, they are the same. Huh? These two are the same. So this we just need to calculate this. Okay. The next things maybe that I need to let you know will be if you have a summating k equals to 0 up to infinity for anything power of k over k factorial will be e of this. So this is actually the definition for the exponential function. So please take note. So this is begin with 0. Okay, this is begin with 0. So if this part, that means you can see that will be 1 plus. Okay, so this is begin with 0. So if you take k equals 0, it will be 1. So then this begin with 1 of this will be equals to e of this. Okay, if you switch over, then you have this one. Will be equals to e of this thing minus this. Okay, this one. Just like that. So if you're aware of this formula or this formula, I think you should able, as well as this standard formula, you should able to solve question A here. So that will be a direct calculation now. So look at the solutions for A. So I think this is straightforward. Okay, first of all, e of this 1 x plus 1. So according to the formula, will be we summating k running from 0 to infinity 1 over. This is if you want to put x here, that will be a small x. That the p of x for Poisson will be e minus lambda k factorial. I think this one no problem. Right. So next things. This is index k, right? So you just take away anything without k. So this one can be taken out. So then it becomes like e minus lambda k equals to 0. So lambda k. So k plus 1 multiplied, this becomes k plus 1 factorial. So these two not the same, right? So this is k. How we want to make it consistent, change k to k plus 1. So what we can do is we just multiply 1 lambda here and this. Because of these 2 lambda can be cancelled. So that's why we can always do that. So lambda power of k multiplying lambda will end up to be lambda power of k plus 1. So then this will becomes, okay, maybe this is the case, e minus lambda Oh, sorry, this is 0. Okay, plus 1. Okay, the next thing will be just a game, playing a game with a symbol. Okay, so what you need to do is you just look at this part. It's just a way of playing with a symbol. So this is begin with 0. So that means k will be running from 0, 1, 2, 3, 4, and so on. So this thing will end up to be, you can see if, when k is 0, you get lambda power of 1, 1 factorial plus lambda 2, 2 factorial plus lambda 3, 3 factorial, and lambda 4, 4 factorial. Okay, so if you expand it, that will be this. Okay, just write, expand it, substitute k equals 0, 1, 2, 3, and so on. So in fact, you can see you can express this in with a running index begin with 1. So this thing, you can see this can also be expressed as this. Okay, so maybe you can change to some other symbol that you can see a better idea. Instead of k, maybe we change to another symbol. What symbol do you like? Or maybe I put h. Okay. Right. So you guys go and think about it. How to change these two. Okay. From here to here, how to change? Maybe what I can tell you is I don't know how to. Okay, you guys go and think about it, how to change the symbol. So usually will be when this is 0, so you just look at the first few terms. So if this is consistent, that will be it. Okay, you can change to this, right? So after this process, okay, so this thing can be written as e minus lambda, then k equals to 1, lambda k, and k factorial. So we just go back to what we have got just now, this one. So when this is 1, so this will be e power of this minus 1. So we just applying this formula. Then this whole things becomes e minus lambda. So this will be e lambda minus 1. Okay, I think that's the answer. So again, actually, this is just the standard calculus thing. So first of all, make sure you know how to switch the running index here, switch from 0 to 1 or switch to other value. Okay. So what you can do is you just expand this thing, these summations, and see the pattern and change the running index here. Okay, B. Using this Chebyshev inequality to show these things. Okay, again, as I said, this is a boson, right? So we know the mean is lambda, so the variance is also equals to lambda. So actually, we can use a more simple version, the macro inequality. Yeah. So okay, macro inequality. Since we are using x here, right? So what, maybe I use another symbol. So okay, I don't want to use the same symbol as in the lecture notes because of we are keep on using x, so it might be a little bit confusing. So I will switch to another symbol, let's say y. So this is actually your macro inequality. Okay. So if you replace this alpha with a g of alpha, where g is an increasing function, that will become your Chebyshev inequality. Okay. So actually, this can be always induced by this Chebyshev inequality. So we are taking this. So next, what you need to do is just manipulate this inequality here. So you from here, okay, I don't know how to see what to substitute into your y. Okay, you guys go and think about it, how to do these things, right? Anyway, in this case, I just show you the answer, how to substitute, what y to be substituted, okay, and how to see how to choose the y, and then you guys have to learn from your own, right? Yeah. So in this case, I just let you know, in this case, you can take y to be x minus the mean. Okay. Instead of lambda, I just put the mean, that will be better, and then square. So this, how to choose this? Okay, you guys go and see the pattern for it, right? Okay, so again, as I said, we take this. So I just take y equals to x minus mu square. In our case, that means which is equals to x minus lambda square in the macro inequality. So then we have this. So if you put it in, okay, and also we have two, right? Y equals to this, and as well as alpha to be lambda square in the Markov inequality. Okay, so then I'm going to have this lambda square p of lambda square less or equals to x minus okay, this is the case here. And also because of the mean is equal to lambda, right? So you can see this part is actually equals to the variance of x, okay? According to it, so that's why this is actually equals to lambda, okay? So that's why from here, then we have the inequality becomes, so lambda square p of this lambda. So, and because of both positive, so what we can do is we can cut this and cut this, right? So that we can simplify it, become this. And once we bring this over, then we can get the answers already. All p x squared equal to 2 lambda less than 1 over lambda. So this is actually what we want to prove. All right. Okay, so like I say, So the main trick will be this, substituting y to be this in the Markov inequality, as well as alpha to be this in the Markov inequality. Okay. How do we know what y to be substituted? That is based on your experience. So you look at the patterns of the questions, and then you see how to make a suitable substitution into the inequality. Okay, since we are dealing with inequality, right? Maybe let's move to the next one. Question 8 first. So these two are the same topic. So let's move to question 8. Okay, this is the one. Okay, what symbol am I using just now? Okay, again, I need this once again. Markov inequality. So again, this is our Markov inequality. Oh, I think something missing here. So again, you look at our pattern here. So you have a x minus ex greater or equals to epsilon. Okay, so this is the case. And again, maybe this is the way you have a variance here, right? You have a variance. Okay, you have a variance here. So then maybe you can try x y equals to x minus mean square. So because of the variance, yeah, maybe that's the way. Okay, and also if you look at here, so this is x minus mu greater than epsilon, right? So if you are taking y to be this, so you want to be consistent, then you can actually square both sides. So this thing will be, how should I say it? This part, right? So this thing will end up to be x minus mu square greater or equals to epsilon. So greater than this, right? X minus mu greater or equals to epsilon. So what you can do is, since there is a square here, square it, you square it. Okay, to be consistent. So that's why here, then that means you should choose alpha to be epsilon square. Maybe that's the way. Okay, you look at the pattern in here, then you see what you supposed to be chosen, which ones to be chosen here. Okay, okay, so let's do it step by steps over here. Again, so what we can do is we can take y to be x minus mu square, okay, and alpha to be epsilon square in the Markov inequality. So I'm going to have epsilon square p of less or equals to e of this. And again, because of both sides positive, right, after we can cancel the square. So here the remaining is epsilon square. So then we have this. And this part again, this is actually the variance, right? No problem. Okay, I got one inequality. So, but this is not what we want. So I got one inequality first. So this is number one. And the next one, this is clear. P of this, a probability is always less or equals to 1, right? I think this is quite clear. This is always less or equals to 1. The next thing, and because of the epsilon is this variance is always a positive number, we can multiply both sides. Okay, so then this thing will be just equals to our epsilon squared. So this is equation 2, inequality 2. So if we summing up these two, right? So we're just taking 1 plus 2. So I'm going to have epsilon square plus sigma square P of this less than 2 sigma square. So if we bring this over, that we got the inequalities already. Okay, so that is the answer. Right. Again, since we are dealing with this Markov inequality, right? Maybe let's proceed. Okay. With question 11. Yeah. Okay. Let's come back to this once again. So this is our Markov inequality. Okay, maybe let's pause for a while to have some discussions over here. Okay, so this is a general form for our Markov inequality, right? Okay, the next thing, just follow what we have done just now over here. Just follow. So if we take y to be e minus mu square, and if we take alpha to be epsilon square, so this one, okay, maybe this one, this equation 1. Okay, just look at our equation 1 here. Okay, just look at this equation 1. So we can actually shift our epsilon to our right hand side over here. Yeah. Okay, so then we have this. As in a perf, we have this P of alpha square. Okay, as in the perf, we have this. So that means the left hand side is always less or equals to the right hand side here. Okay, this is the case. So the next questions, just to say that we just focus to this part, the less than or equal. So you can see, just a remark for you guys, this, maybe I use another color, so maybe this color. This can not be replaced by this. Okay, just to let you know this, because they do have random variables x with equality holes. So that's why we cannot just simply say this is strictly greater. Yeah, of course, in certain case, we can have a strictly greater case. However, we can have some random variable such that this equality hold. Okay, so that is a purpose for it. So this is you can see example in question 11. Okay, so in question 11, just to demonstrate, is an example to demonstrate you cannot replace this with a strictly less than. Okay, because we can always construct a random variable x such that the equality holds here. Okay, so now you know what to do with this question 11. Okay. So that's the question 11. So like I said, we can always construct an example such that the left-hand side equals to the right-hand side. Yeah, although, of course, we do have some random variables such that left-hand side strictly less than the right-hand side. But we do also have plenty of random variable with left-hand side equals to right-hand side. So question 11 is one of the examples. So I thought this is quite straightforward once the answer is given. Okay, anyway, let's look at it. So the solution. Okay, I just briefly go to the solutions. Okay, show that there exists a random variable x taking value -1, 0, and 1 such that the left-hand side equals to right-hand side for some positive alpha. So what we can do is make it easy. We take alpha to be 1, and also we define this px equals to -1 is equals to sigma square over 2, and px equals to 0 to be 1 minus sigma square, and px equals to 1 is equals to sigma square over 2. Yeah, of course, before that, you need to verify whether this is, I think I just put an extra remarks here. So, indeed, before continue to the next step, you need to ensure P is a probability. Okay. You need to check this is a probability. You cannot just simply construct something, yeah, and then to proceed. Okay. Again, I suppose you guys already know the procedure to verify whether P is a probability or not. So anyway, I think it's quite straightforward. What we can do is we can always assume this sigma square to be less or equals to 1. Okay. we take alpha to be 1, and also we can take, I think we need one additional, we take sigma to be 0 to 1. Maybe we can actually also take greater than 0. Cannot be 0. Can it be 0? Maybe 0 to 1, doesn't matter. So for example, you can take half to be just to ensure this thing is positive. Okay, we take alpha as 1, and if we take sigma square is in between 0 to 1. So with this, I think with these conditions, then it can be easily verified that this P is a probability measure. Okay. Okay, we define it. I think next one by one, I think it's quite straightforward. We can do it step by step. So EX, so I think it's clear, right? So it's -1 multiplying sigma square over 2 plus 0 multiplying 1 minus sigma square, and plus 1 multiplying sigma square over 2. Yeah, minus. So then I think it's clearly, so the value must be 0. Okay. Then the next one, I think also quite straightforward. So the variance of x will be -1 square sigma square over 2 plus 0 square plus 1 square. So then, yeah, this is the variance. So we got it. Okay. Okay. So I think it's clear that hence we can have this. Okay. P of x minus means greater or equals to alpha b always equals to sigma square or alpha square. Okay, so if you substitute everything inside, so that means actually you can easily x minus 0 greater or equals to 1. This part, because of this is actually P of. So when this is greater than 0, that is actually this 2, right? So this is actually P of x equals to 1 plus P of x equals to -1. So that's why this is equals to sigma square. Okay. Okay, so that is question 11.
Yeah, actually, I asked this question because I felt like it's very easy to show this, but then to come up with the random variable is, well, it's a lot harder.
Yes, indeed, it is true. It's true. Like I said, it's just like a reader. Okay, if I don't reveal the answer to you, so it's very hard for you. But once I give you the answer, yeah, you see, that's very obvious. So that's why I don't know what to say. Actually, it's all based on your experience. Okay, so if you have seen, you have done more exercises, you've seen more example, then you have a better idea of how to construct all these things. Okay, so that's why just like the previous questions here, right? Just like our previous question here. So you guys might wondering, how am I supposed to substitute this y and alpha? I'm really sorry, I can't tell you how. Just based on the patterns of the questions, and then you choose the right thing to substitute inside. And most of the time will be try and error. Yes. Okay. You try and error, then you do it. So once you have done more exercises, you become more experts, then the number of try will be less. The only thing that I can tell you. Okay. Right. Okay, so like I said, this question is again quite interesting. So if the answer is given, then it's so straightforward. If the answer is not given, then it might be quite difficult. In fact, I think after this, right, you guys can go and choose your own answer. You can construct it. You can just do a slight modifications over here. You can come up with another examples. Okay, just go try to do it, right? This is the most perfect case. Okay, you can do some modifications over here, right? Okay, so next one, question 10. Okay, again, since we are dealing with this inequality, right? Okay, let's look at it first. Question 10. I don't know what's the issue with the solution, because to me, I thought it's quite straightforward already. Yeah, although it's not easy. Not actually, it's not difficult. It's just that looks complicated. So yeah, let's look at the answer. Maybe I directly go to the answer. Okay, so this is the Cauchy-Schwarz inequality. Yeah, Cauchy-Schwarz inequality. Okay, E of magnitude of X and magnitude of Y less or equal to this. Okay, whenever X and Y belongs to L2, that means it's E of X squared is finite, E of Y squared is finite. So this is always less or equal to, and equality holds if and only if then X will be equals to S X will be equal to alpha Y almost surely for some constant. Okay, since we are dealing with modulus, right? So we can assume X greater than or Y greater. So if you don't want to assume this, or you replace X with modulus of X and Y with modulus of Y. So that means you just need to put a modulus of X. So you always need to put a modulus inside there. Okay, so quite troublesome. So that's why it doesn't matter. I can just always assume both X and Y are non-negative. So yeah, I think maybe put a ruler here so that you know which part I am discussing now. Okay, so this part. So okay, so you assume this or replace X with this. Okay, if you don't want to do that, so it's quite troublesome. Okay, if Y equals to 0, I think it's clear. Y equals to 0, so both left-hand side and right-hand side equals to 0. Okay, if Y equals to 0, maybe I put it over here. I think I can put this one. Okay, when Y equals to 0, so you can see left-hand side equals 0 and also equals to right-hand side. So that's why this is an equal case. So no problem. So that's why then we proceed to Y greater than 0. Okay. So this is we got it. Okay. Y equals 0. Forget it. I don't want to mess it up. Okay. So when Y equals 0, so left hand side equals to right hand side, I think equality holds. That's what I mean here. Okay, next we just assume y is non-zero, positive. Okay, I think this part straightforward. So that is just you square x squared minus 2 alpha y squared plus alpha squared y squared. So then you have this. Okay, next, that is just a straightforward calculations. Oh yeah, I think I have a mistake over here. Sorry, I have a typo here. Please make a correction, sir. How? This thing's supposed to be y squared. Okay, maybe please make corrections. So this is supposed to be not both. Okay, it's supposed to be ey squared. And okay, this one's supposed to be ey squared. Okay, this part. Okay, this one supposed to be ey squared. Okay, maybe add both. Ey squared multiplying ey squared. Okay, this part. Please make corrections. So actually, it's not difficult. What you just need to do the some calculation. You can verify. So okay, you begin with here. So both left hand side, right hand side, you just need to divide it by the e of y squared. Yeah, and after that will be just completing the square. So you get this, then you will get these calculations. Okay. So maybe I would just briefly work out the calculations over here. Okay. So you can see. So look at the, maybe this one, not this. So the right hand side is equals to e of x squared minus 2 alpha e of xy plus alpha squared e of this. So if you divide it by x squared, right, so that will be this. So, and this one will end up to be 1. Okay, so that will be this. And next, I just need to rephrase this. So just look at the first two terms. Okay, maybe I just switch the color so that you can see the patterns. Okay, I'm using a green color. So e of x squared over e of y squared here. Okay, next thing. So this will be equals to, okay, so the green color terms remain the same, e of x squared, e of y squared. So you look at these two. So what we can do is we just minus one extra terms. So this one. Square. Okay. And plus another one. And together with these terms. Okay, so you, Okay, so these two remain the same. Okay, these two, right? So maybe what you can do is maybe not remain the same. So these two, you can becomes like this. So it will becomes so this part will becomes you just combining them. So you will get this will becomes ex square ey square minus exy square divided by ey square ey square. Okay, so this will become this, and this part then it will become this. Okay, so this is how we can get these calculations over here. So again, you just look at the detail for it, so you will get the calculations. Okay, then let's go back to our solutions once again. Okay, so this is our solutions here. So again, sorry, as I said, there's a type error here. So this is supposed to be y square instead of x square. So this is how we can get it. So this is actually this part. This part is this part. Okay, these two are the same. So this is how we can get this is equal to. So you can see the next. We just need to verify one by one. Yeah. So since the left-hand side and the first terms of the right-hand side are non-negative, so I think it's clear. These terms is non-negative, right? This term also, because you have a square, the smallest value will be 0. Okay, this is non-negative. So that means we will get this part must be greater or equals to 0. Okay, so this is how we can get the inequality. So if these two things equal, so that means this must be equals to this one. No, I think if equality holds, so this one must be equals to 0 because of that's gone. So this one must be equal to 0. So when this one equals 0, then this must be equals to this almost surely. I think I did I have this discuss this before? Maybe just a remark for you guys. Okay. So that's the meaning. Okay, what you can do is you can replace it. So when we say let's say one random variable z equals to 0 almost surely, okay, or maybe equal, make it easy. Okay, we can see two random variable. Z equals to v almost surely. Okay, so this is just simply means that I think we just say if and only if the probability of x y not equals to v is equals to 0. Okay, so that means z might not be equals to v in all the values. However, in the portion whereby z not equals to v, its probability will be 0. That means the likelihood to happens will be 0. Okay, the chances. So this is the case for it. So according to here, then you can see it. So that's why in these questions, also we know this. Okay, B. If E of Z minus V is equal to 0. Yeah, I think so. So then this one will be equal to B almost surely, or okay, maybe I put it down there, or the probability of Z not equals to Y is equal to 0. Okay. Okay, so I think it's almost done, except I have one more question 6, but it's already 7:30. Maybe let's take as usual. Let's take a break for half an hour. So maybe we continue to question 6 in the second section for our lecture. Okay. After discussing question 6, we carry on to our chapter 5. Right. Okay. Again, let's take a break so we can continue the second section at 8 o'clock.